Okay, we are doing lesson 6.4, and we're going to do examples 1 through 3, and it can be found on pages 268 and 269. Now, everything you see is a function. Every input has only one output. Every X has only one Y. So everything you're going to see is a function. We need to decide, is it a linear function or a nonlinear function? So on Monday, they gave us tables. We were working with linear and nonlinear functions in tables. And sometimes the table was given to us horizontally. So when we're given a table, this is a function. We want to know if it's linear or nonlinear. So I need to look at my changes. Let's take a look at the change in X. 3 to 4 is +1. 4 to 5 is +1. 5 to 6 is +1. My change is +1. These are the same. Therefore, my change in X is constant. My change in X is +1. It's constant. Now let's take a look at our change in Y. +2, +2. My change in Y, my changes are the same. Therefore, they are constant. So my change in Y is constant. Now this should look familiar to you. Change in Y over change in X. This is known as the slope or the rate of change. So we can say as X increases by 1, Y increases by 2. Since my change in X is constant and my change in Y is constant, we have a constant rate of change. Therefore, this is a linear function. Okay, let's look at another one. This time they've given me a vertical table. Now this is a function. Every input has only one output. Every X has only one Y. So it is a function. We want to know if it's a linear or nonlinear function. So to do that, we have to look at our changes. So our change in X, +3, +3, +3. So our change in X, they're all +3. They are the same. They are constant. So my change in X is +3. Now let's take a look at our change in Y. +3. Whoa. +5. +7. These are not the same. These are not constant. So my change in y, do I use +3 or +5 or +7? I don't know. It's not the same. I don't know which one to use. Therefore, my slope or my rate of change is not constant. So let's take a look at that. As x increases by 3, because that is constant, y, it is increases by different amounts. So when I look at this is constant, but this is not. So we do not have a constant rate of change. Constant rate of change. This is not a constant rate of change. Therefore, this is a non-linear function. Okay, so we know what a linear function and a nonlinear function look like as a table. Let's talk about what they look like as graphs. So this is a linear function as a graph. It's a line, it's straight. This is also a linear function as a graph. The graphs are lines. That means they're straight. Therefore, they are linear functions. And that kind of makes sense. My slope is constant for the whole graph, right? Here, my slope is 0. It doesn't matter which points I use. My slope is 0 across the graph. My rate of change is 0 across the graph. It's constant for the whole graph. Same thing here. If we look, this is kind of up 1 over 2, up 1 over 2, up 1 over 2. My slope or rate of change is the same or constant for the whole graph. So if I have a constant rate of change for the whole graph, it's going to be a straight line. It's going to be a linear function. It's a constant rate of change. So let's take a look over here. And let's take a look at this one. Both of these are functions, but they're not lines. They're not straight. So the graphs are not lines. They're not straight. Therefore, these are nonlinear functions. And that kind of makes sense because my rate of change or my slope is not constant. My slope from here to here is much different than my slope from here to here. This is a much flatter slope. This is much steeper. My slope is not the same here as it is here. So my slope or my rate of change is not constant. Therefore, my graph is not a line. It's not straight. So this is a nonlinear function. Same thing here. The slope here is positive. The slope here is negative. My slope is not constant. This is not a line. It's not straight. So it's nonlinear. So we know what linear and nonlinear functions look like as tables. And we know what linear and nonlinear functions look like as graphs. Let's talk about what linear and nonlinear functions look like as equations. Okay. Each of these equations that you're going to see is a function. But we need to decide, is it a linear function or a nonlinear function? So our first equation, y equals 3x. We need to decide, it is a function, but we need to decide, is it linear or nonlinear? Well, if it's linear, you can write it in slope-intercept form. Y equals mx plus b. Is this in slope-intercept form? Yeah. The b is there. It's just invisible. It's just invisible. It's there, but it's invisible. So this can be written in slope-intercept form. Can be written in slope-intercept form. Y equals mx plus b. Therefore, this is a linear function. It is a linear function. Let's do another one. Y equals 4 times x minus 1. Now, when you first look at this, it is a function, but it does not look like it's written in slope-intercept form, does it? Y equals mx plus b. Well, let's distribute it out and see what happens. Y equals 4x, multiply 4 times negative 1. Holy smokes, what do we have? Is it now written in slope-intercept form? It is. Can be written in slope-intercept form. Y equals mx plus b. Therefore, this is a linear function. Let's do another one. Y equals 4.7. Well, if we graph this, 1, 2, 3, 4.7. This is y equals 4.7. The slope is equal to 0. So we want to know y equals 4.7. Is it y equals mx plus b written in slope-intercept form? Well, y equals, my slope is 0 times x, and my y-intercept is 4.7. We don't typically write 0x because that's 0. The mx is there. Mx, it's there. It's just invisible. So y equals 4.7. This can be written in slope-intercept form. It's just that the mx is invisible. It's 0. Therefore, it looks like a line to me. This is a linear function. I have only 2 more examples for you. Okay, we have 2 more examples. The first one, y equals 4 over x. Can this be written in slope-intercept form? I don't know. Let's play with it and see. I want it to look like y equals mx plus b. So I need to get this x up here. So to do that, I'm going to use inverse operations to get rid of my x in the denominator. What I do to one side, I must do to the other. So xy equals, these cancel, 4. Okay, but I need it in y equals mx plus b format. I need my y isolated. So I need to get rid of this times x. So I'm going to divide by x. What I do to one side, I must do to the other. All this is circular math. I keep getting the same thing that I have. So this, I cannot get this to look like this. This cannot be written in slope-intercept form. Therefore, this is a non-linear function. I cannot get my x up in the numerator unless it's attached to the y, and I need my y isolated. So I can't get it to slope-intercept form. It is a function, I just can't get it into slope-intercept form. So it's a nonlinear function. Now, this is different than this. Y equals 5x over 2. Can we get this into slope-intercept form? You have to know how to manipulate fractions here. Y equals, these are the same problem. Same problem. Is this now written in slope-intercept form? Yeah, because that plus b plus 0 is invisible. This is written in slope-intercept form. This can be written in slope-intercept form. Therefore, this is a linear function. So don't let this fraction confuse, don't get this fraction confused with this fraction. Here, x is the denominator. Here, x is still in our numerator, and we can rewrite that fraction into slope-intercept form. So that's what we're doing today. Everything you see is a function. You know what a linear and nonlinear function look like as a table. You know what linear and nonlinear functions look like as graphs. And now you know what linear and nonlinear functions look like as equations.